Every day it's like a never-ending sequel. Apply bitwise operations to make strings equal. Let's go ahead and get right into problem 2446. So you're given two zero-index binary strings s and target of the same length n. You can do the following operations on s any number of times. You choose two different indices I and j, where 0 is less than or equal to I, j is less than n. So you choose two indices which are within the boundaries of these zero-index binary strings. And you can simultaneously replace s of I with s of I or s of j. Okay, so s of I becomes s of I or s of j. And that was outside the boundary. I apologize. And s of j becomes s of I XOR s of j. Now, if you don't know what these operations are, then likely you shouldn't be approaching a bitwise operation problem like this, right? Because it's very common to receive this style of problems, right? Like a bit mask, bit operation problem in a interview setting. And it's even more common when that interview setting has to do with some low-level software, hardware, engineering role or whatever, right? And with this information, I can kind of determine likely what my course of action is going to be. And that is we're going to create a truth table, and we're going to look at different values and different value pairs of s of I and s of j, and what that implies about what bits we can switch, what bits we can't switch, what are the consequences of committing these operations, right? And that's kind of knowledge that may not be initially intuitive, but if you've had some exposure to these type of problems, it tends to usually make itself quite transparent. That's how you're going to approach this problem. But that's kind of a side note to just describe kind of the background you need to solve this, right? If you start seeing ORs and XORs and ANDs and bits and bytes, right? If the problem has all those words in it and you don't know what that means, you're not going to be able to solve it. So you need to learn that basis before you approach this, okay? So with that said, for example, if s equals 0, 1, 1, 0, you can choose I equals 0, j equals 2, and you'd simultaneously replace s of 0 or s of 2, right? X of 4 or whatever. Yeah. Return true if you can make the string s equal to target, or false otherwise. Okay, so you have this source string s, right? Right, so you have s equals 1, 0, 1, 0. And you want to make it equal to t, which is 0, 1, 1, 0. Now, what the issue is within the context of this, right, is that, well, this 1 needs to become a 0. So there's an error there, right? This 0 needs to become a 1, and then these two can stay the same. So we have to use this operation before, right? We choose two indices and carry out this operation so that bits can be switched, right? Or bits won't be switched. All these bits, man. I can't handle these bitses. Okay. So let's go ahead and draw out the truth table to see, let's exhaust all possible combinations of 1, 0 pairs for these bits and see what the outcome is, and then determine if we can integrate that into a solution, determine whether or not it's possible to take s and turn it into t. So let's draw out the truth table for this system. So for this system, we're going to have s of I and then we're going to have s of j. And then after we do that, we're going to get some outcome, right? The new s of I and the new s of j. What I'm basically saying is, the left side is what s of I was before, and the right side is what s of I will become, right? once you do this operation. So what are the possible combinations? What are all the values that S of I and S of j can be? Well, each one can only be 0 or 1, right? So S of j can be 0 or 1, or 0 or 1, or 0, 0, 1, 1. That's just a little trick. There's just a significant delay, and I apologize about that. I don't exactly know what's going on. But S of I and S of j, right? S of I can be 0, 0, 1, or 1. S of j can be 0, 1, 0, 1. Basically saying these are all the combinations, right? There's no other combination of S of I and S of j. These are all the cases that you would see. If you were to carry out this operation, then what would be the result? Well, if S of I is 0 and S of j is 0, S of I becomes S of I or S of j. So this is still 0, right? Because 0 or 0 is 0. Basically, the OR operation, if you're not familiar with it, which you should be to do this problem, but the OR operation is if one of the two arguments is true, if one of the two arguments is 1, the new thing becomes 1. Otherwise, it becomes 0. Are one of two of these arguments 1? No, so it's 0. Are one or two of these arguments 1? Yes, so it becomes 1. Are one of two of these arguments 1? It becomes 1. Are at least one of two? And are at least one of two of these arguments 1? Yep, so it becomes 1. Now for S of j becomes SI XOR SJ. So that means that one of them needs to be true, but not both. So if one of them are true, then it's true. But if both of them are true, then it's not true. If both of them are false, then obviously there's nothing, so it's still false. So 0, 0, S of j would be 0 because they're both false. Is just one true? Yeah, just one is true in this case. Just one is true in this case. And both are true in this case, so this is 0. So this is just a basic truth table. You should probably be familiar with this, but this is where we're going to pull most of our knowledge to determine how we're going to manipulate S to get T. So, XOR basically just means that one can be true, but not both. Or just means one of them is true. At least one of them is true. Okay. So we kind of have what? We kind of have 4 different situations we have to deal with. If we have S and we have T, and we're trying to get S to go to T, right? So we're trying to get S to go to T. T is the target here. I'm going to use T going on forward. And we kind of have 4 different cases we need to think about. If S is 0 and T is 0 at that same bit, right? If S is 0 and T is 0 at that same bit, then we don't need to concern ourselves with any changes because it's already right. For example, here, right? We don't need to swap this bit because it was a 0 and it becomes a 0. If S was 0, then it becomes a 1. We need to think about, this is something we're going to need to think about, right? Because it was a 0, S was a 0, it needs to become a 1, so we're going to need to do something with that bit in order to swap it, right? And we're going to need to do something in terms of these operations to determine what we can do to make this 0 turn into a 1. If S was a 1 and it's going to end up being a 1, again, there's nothing we need to do here because, it was a 1 and now it's going to be a 1. We don't need to touch that bit because remember, we can use that bit in order to change another bit, but we don't need to change that bit. And then the last thing is if it was a 1 and it needs to become a 0, right? So that's also something we're going to need to figure out. So let's first think about turning a 0. Let's move this over here because we want a complete picture of everything that we've done doing here. Okay. How do we turn a 0 into a 1? How does one do that? Well, I guess the question becomes, where in this truth table does a 0 become a 1? Okay, here it was a 0 and it stayed a 0, right? 0 stays a 0. 0 stays a 0. 0 becomes a 1. So whatever I did here turned a 0 into a 1. This was a 1, it stays a 1. This was a 1, it stays a 1. And I'm just going through them right now. I apologize about the delay, but you'll see in a second. 0 becomes a 1. This was a 1, it stays a 1. This was a 1, it becomes a 0. Okay. So there's a little bit of a delay, and I apologize. But you'll see it here, right? So there's kind of two cases, right? There's two cases where I can turn a 0 into a 1. I can choose an S of I that is 0 and an S of j that is 1. But I can choose an S of I that is 0 and an S of j that is 1. And then I will make that S of I 1 and it won't change j. Or I can take an S of I that is 1 and S of j is 0 and turn that 0 into a 1, right? So essentially I need S of I equal 0 and so j equal 1, or I need S of I equal 1 and S of j equal 0. So these are kind of my two options here, right? To turn a 0 into a 1, either I choose an S of I that is, I make the 0 that I'm trying to turn into a 1, I set it to I set its indice to I, and then I grab one of the j's that's a 1 and convert it. Or I select a j that's 0 for the 0 that I'm trying to convert, and I select another element that's a 1, and that'll convert this 0 to a 1. So I either need to use, to turn a 0 into a 1, right? To turn a 0 into a 1, I either need to use the case where I use a 1 that's going to end up being a 0, or I use a 1 that ends up being a 1. Right? What I'm basically saying is I just need a 1, right? I need a 1 from S, right? Because this pointer function here is saying something on the left, right? An S. So I need an S that becomes a 0 later, or I need a 1 that stays a 1, right? So I'm basically saying in order to convert a 0 to a 1, I'm going to need a 1 in S that becomes a 0, or I'm going to need a 1 in S that becomes a 1, right? Because I'm going to need to use that other thing in order to turn the 0 to a 1 by doing one of these operations here, either the OR or the XOR, depending on if I want it to be J or I, okay? Now, let's think about how are we going to turn a 1 into a 0. So now we want to think about, well, how are we going to take a 1 and turn it into a 0? Usually you want to take a 0 and turn them into a 1, right? You want to take someone who's at the 0 and you want to turn that person into a 1, a winner. But now we want to think about how we're going to take a 1, someone who won already, and turn it. I'm just joking around. That's me trying to be funny. That's what happens when you spend so much time doing Leetcode and being a nerd. Okay. So in order to convert a 1 to a 0, where does that happen in here? Let's use this truth table again, right? Because this truth table determines what occurs when you do these operations. All right, now, so I'm just going to quickly go through them. So 0 stays 0, 0 stays 0, 0 turns to a 1, 1 turns to a 1, 1 turns to a 1, 0 turns to a 1, 1 turns to a 1, and 1 turns into a 0. So it turns out there's only one case, okay? There's only one case where we can take a 1 and turn it into a 0. And that is here, this last line, right? If I take an S of I, right? If I take an S, always do that. If I take an S of I equal 1 and S of j equal 1, then S of j will become 0. Okay? So formally, if I want to think about that again in terms of this system, well, if I want to turn a 1 to a 0, I'm going to need another value that's a 1, right? So I'm going to need to take a 1 that stays a 1 or a 1 that turns into a 0. Right? So in order to take a 0 and flip it into a 1 to resolve that, we need to find out if there's a 1 that becomes a 0 or a 1 that becomes a 1. And in order to take a 1 and convert it to a 0, we're going to need to find a 1 that converts to a 0 or 1 that converts to a 1. It's kind of the same thing, right? We need 1s and S in order to do this stuff, right? We need a 1 to flip stuff. We need a 1 to turn something into a 0. We always need another 1 in order to do what we need to do, okay? Now, what's weird is this tree here, like, resolves easily, right? Because to get a 0 to go to a 1, right? To get a 0 to go to a 1, what do you need? You need a 1 to go to a 0 and a 1 to go to a 1. So if we wanted to, like, paint this tree, saying, okay, we want to make a 1 go to a 0. Right? This delay is ridiculous. I don't know what the heck is going on. All right, we want to turn a 1 to a 0. Well, to turn a 1 to a 0, you're going to need either a 1 or let's do 0, 1. To make a 0 turn into a 1, you're going to either need a 1 that turns to a 0 or a 1 that stays a 1. Okay, this is self-resolving, right? Because this is a 1 and it stays a 1, so no matter what, this is a 1. So this is a 1 here. So we don't need to keep going down that tree. But what about a 1 to a 0? Well, in order to get a 1 to get to a 0, we need a 1 that goes to a 0 or a 1 that goes to a 1. Again, this is self-resolving. But the weird thing is about this 1, 0 case is that 1, 0 is based on 1, 0. So in order to get a 1 that goes to a 0, we're going to need either a 1 that stays a 1, but if we don't have that, we're going to need a 1 that goes to a 0. So in order for yourself to turn to a 0, you need another thing that's like you that turns to a 0. So now we have this like weird recursive relationship because in order to get a 1 to go to a 0, I need another 1 that goes to a 0. But in order for that 1 to go to a 0, it's going to need another 1 to go to a 0, and so on and so forth. Right? So the issue is since they're based on each other, right? If you had, for example, S equals 1, 1 and T equals 0, 0. Okay? So just a quick example here. You would say, all right, in order to turn this 1 to a 0, I'll use this 1. So then I'll do this operation here, right? I'll do 1, 1. I'll do 1, 1 and convert it to 1, 0. My head's covering it, right? But if I do this operation here, I can take 1, 1 and convert to 1, 0. So I can convert this one to the right thing by doing this operation. So I do 1, 1 and it'll become 1, 0. Right? But now I need to make this 1 turn into a 0, and there's no way of doing that because I need another 1 that turns into a 0. So the only way I can make a 1 turn into a 0 is if there's either a 1 that stays a 1 or at some point, right? This is the hardest part of the problem. At some point, there has to be a 0 or a 1 that wants to become a 1. Right? The only way I'm going to get to convert myself to a 0 is if I'm a 1, the only way I get to be a 0 is if I attach myself to another 1. There'll only be another 1 if that 1 wants to be a 1 by the end. Otherwise, I'm never going to get to work with it. And if I don't work with it and I convert, then it might need me, right? So the idea is, well, the only way this 1, 0 here will become a 0 is if it has a 1 to match with. But that'll only be if by the end there's a 1 for it to match with, which is why there's an issue in this problem here, right? Because as soon as if there's 2 of them, as soon as your neighbor finishes, it's going to need you, you're going to need it. And if you need it and it needs you simultaneously, you're not going to be able to convert both of each other, right? Because you need 2 1s. So 1, 1 will turn into a 0, and now this one is left stranded. So this 1 that turns into a 0 eventually is going to need someone that wants to be a 1. So who here in this system wants to be a 1? that could be the left child. Well, that's essentially this link here. Right? Because this 0 will want to become a 1. And this 1 will want to become a 0. So they can work with each other directly in this loop. And that way they'll be able to satisfy each other's condition. Because this thing wants to become a 0. And this thing will eventually become a 1. So this will become a 1, and this 1, 0 can base itself on it. So now that you have this cycle, you're able to sustain the system, right? For example, if you had instead ST equaling 0, 1, 1, 0, right? Well, in order for a 0 to be a 1, do you have a 1 that wants to become a 0? Right? I have this 1 that wants to become a 0 here, and I have a 0 that wants to become a 1, so I have these two cases inside of my system, right? So now we can work with each other, right? So if I want to become a 1, I need a 1 that wants to become a 0. So I say, okay, I'll XOR with you. That's this 0, 1 here, which will turn this into 1, 1. And now this thing can ask, well, I need someone that's a 1 that wants to become a 1. Well, this thing will say, well, now I am a 1. Right now with this loop, it'll say, well, now I am actually a 1 that you need. And I'm already done with what I need because you're my child. Since you're my child, I've already finished. So since I finished, now you can go. And now it's 1, 1, which is this top case, right? Which is 1, 1. Converting this to this last one to a 0. So there you go. So now you have a loop relationship. So really, the idea is if you talk about this thing in terms of children, right? So if we put pointers on all of these, if you have a 1 to 0, if you have a 1 to 0, you need a 0 to 1 or a 1 to 1. And if you have a 0 to 1 constraint that needs to be satisfied, you need a 1 to 0 or a 1 to 1. And there you go, just like that. Okay, so what we can do then is just map all of these constraints and then return that in the system, okay? So I'm gonna call this from to, and then what I'm gonna do is, and I'm gonna say for from, because from is S, and to in zip, S and target. So I'm basically saying it goes from S to target. I'm going to say from to of where I'm going from is would be the order of from minus the order of 0. So it's offset from 0. And the order of to minus the order of 0. Let's say plus equal 1. Okay. And then what I do is I'd ask this question, right? If I have a 1 that goes to a 0, I'm going to need a 0 or 1 or a 1 to a 1. Right? So if there's something from 2, so if there's something from 1 that goes to 0, and there's not something that goes from 0 to 1, and there's not something that goes from to 1 to 1, I'm going to return false. If I have something that needs to be swapped from 0 to 1, and there's not something from 1, I'm just writing, because it's kind of confusing, so I'm just writing down these conditions. So if I have 0 to 1, right? If I have 0 to 1, I need 1 to 0, 1 to 1. Okay, so if there's not a 1 to 0, and there's not a 1 to 1, return false. Otherwise, we return true. Oh, this needs to be 0 times 2. Okay, cool. So there's a way to make the solution slightly shorter, but it doesn't affect the runtime. It doesn't affect the space complexity. But if you want to be cute about how you understand this, there's a further way to simplify this. But just to kind of give you the runtime and the space here, and then you can think about the shorter, we can cover the shorter solution after if you want to stay. If we let n equal the length of s, which also equals the length of target, right? For time, well, we just create this. This takes constant time, right? Because it has nothing to do with the length of the string. We just create a 2 by 2 array. We have to look at each character in the string. So there's n characters in the string, n bits in the string. So we have to look at all n bits. And then we just ask 2 questions about whether or not these cases are true or not in order to determine if we can make this conversion. So for time, that's O of n. And then for space, well, this is a 2 by 2 array, and it's a 2 by 2 array independent of how large n is, right? Now, I guess you could make an argument that count. Well, you could just make this 1 because something needs to exist. So as long as that's 1, this should work. So now it doesn't scale, right? It's not like log n bits because you have all these bits because you have to acknowledge how long it doesn't matter. What I'm saying doesn't matter. It's constant, right? Because I'm just creating this from to array and its only elements are either 0 or 1. So that'd be big O of 1. And that would be your run in space complexity, time and space complexity for this problem. But a further simplification that you'll realize is, well, if you have 1 to be 0, you need a 0 that converts to a 1 or a 1 that converts to a 1. That basically means that there's a 1. Another way of writing this is that there's a 1 in the target. Okay? And I don't know exactly what the reasoning is behind this, but it's just something that you'll notice. If you want to have a 0 turn into a 1, you need there to be a 1 in the source. Right? Because this arrow, right, means that you take something in S and turn it into 1 in T. You take 1 in S and turn to a 1 in T. You take a 1 in S, you turn to a 0 in T. You take a 1 in S and you convert it to a 1 in T. So these are basically saying there's a 1 in the target and there's a 1 in the source. Now, if you don't have a swap, right? If you don't have a swap, what does that mean? That means either they're all 1s or they're all 0s. So what would be the max of S and the max of T have to do with this problem? Well, if you take a 0, if you need there to be 1s in the source, that means that the max of S equals 1. That would mean that there's a 1 in the source, right? Because there has to be just 1 in the source, so the max of S would be 1. If you need there to be 1 in the target, that would mean that the max of T equals 1. But if you have no swaps, you don't need there to be any 1s, right? If it's all 0s or all 1s, it doesn't matter how many 1s there are because there's no swaps, right? We only need to consider the number of 1s in the system if there's a swap. So if they're all 0, then the max of S will be 0 and the max of T will be T. So if these two things are equal, then the solution exists. As strange as that sounds. So we don't need any of this. We can just say return the max of S equals the max of t. Period. There you go. All right, guys. Hopefully that was a little bit. Hopefully that explanation was good enough. It's kind of a difficult problem, and I don't even know exactly how I figured it out, to be honest with you. I just thought through a few examples when, especially the 1 to 0 0, and thinking about, well, since these things are swapped, something can't be based on itself. It eventually has to be based on something at the end that converts to that thing. And yeah, that led me to a solution. All right, peace out.